Hello, everybody. So today we're going to be talking a little bit about electric and magnetic fields, and just go into both of those. So we'll start with electric fields. So we'll start with the basis of it. So there's two types of electric fields. There's uniform electric fields, and there's non-uniform electric fields, and both of these use different formulas to find the electric field strength. So with uniform electric fields, the electric field strength, what that means is it's usually that happens between parallel plates, and the electric field strength is the same at any point in the diagram or in the electric region. So a question might give you the full potential difference and might give you the full distance across those, but it will ask you to find the electric field strength at like, let's say, a random point in between them. But they're just trying to trick you. You gotta know that the electric field strength used for the full voltage over the full distance, so is the electric field, and that's not gonna change. So that's their equation for this one. Electric field is the change in voltage over the change in distance. Now, non-uniform electric fields come from a point charge. Here I've drawn a negative point charge, and the equation to find the electric field strength at any given point from the point charge R is kq over r squared. And what this basically tells you is that the closer you get to the point charge, the stronger the electric field strength is. But it's if let's say you increase your distance from the electric charge twice, then the electric field strength is going to decrease by 4 times. So it's inversely proportional. And one thing you have to know about these is the field arrows always indicate where a positively charged object will go. So here it's negative, so a positively charged object will run towards the negative point charge. In this case, we have a uniform electric field, and these ones run from positive to negative. So our electric field lines will look something like this. Those are our electric field lines because this is where a positively charged object will go from the positive end to the negative end. And that's basically the basis of the uniform and non-uniform electric fields. Alright, so I've switched pens because the other one wasn't really working too well. In this example, we have 3 different diagrams. We want to determine the electric field strength at point P at each of the points. So I forgot to add it here, sorry guys. So to determine the electric field direction with question A, we know in a uniform electric field, the field lines run from positive to negative. But in this case, we're not immediately given a positive and negative plate, so we need to figure that out by looking here. So right here, the greater end of the battery that produces the voltage is going to be closer to the positive plate, and the shorter end is going to be closer to the negative plate. So from there, we can create this. Now that we know this, at point P, it's going to run from positive to negative. So it's always where a positively charged object will go. So it's just the electric field direction is this, arrow upwards. So now for B, this is more of a vector question. So again, where would a positively charged object go? We have to look at each individual charged sphere. Here we have a positively charged sphere. At point P, let's say a proton at point P would get repelled by this, but attracted by this. Because protons are positive, they get attracted by negative, but repelled by a positive charge. So if it gets repelled by this, but attracted by this, then it's going to create a vector going down west of south or south of west, depending on which is stronger. That's irrelevant. So that's going to be roughly the electric field direction. Now for this one is a little bit more, you have to think a little bit more. So at point P, we have a positively charged sphere and a positively charged sphere, and point P is in the middle of them. So firstly, looking at this sphere, the electric field direction would be this way. Because it's repelling the positively charged object, and here the electric field would be this way. But one thing I forgot to mention is that Q equals Q, and the charges are the same. So according to our formula, E equals KQ over R squared. If the distance between the two spheres and point P is the same, and the charges are the same, then everything else will be equal. And since these electric fields oppose, the total electric field strength is 0, and so this is a electric field that has no direction because they cancel out. So here we have a numerical example for the first time in the video, and what we're wanting to find here is the net electric field strength at point P. So the net electric field strength at point P is going to be a function of what this charge has, what effect this charge has, and what effect this charge has. So both charges are 3 microcoulombs, but this one's positive 3 microcoulombs, this one's negative 3 microcoulombs. So first thing to do is to determine which direction the electric field is being produced by each sphere. So by this positively charged sphere, the electric field is away. So electric field is this way. And by this negatively charged sphere, it'll attract a positively charged object, so it's also this way. So in the end, when we find both individual electric fields, we're going to be adding them rather than subtracting them like we did in this example. So we'll start actually finding the electric field. Let's call this Q1, and let's call this Q2. Let's find the electric field that Q1 produces on P. So we know that this is non-uniform. So we know that the formula for non-uniform electric fields is KQ over R squared. So we know the radius is 0.125 meters. We know Q is 3 microcoulombs, which is just 3 times 10 to the negative 6 coulombs. We know that our coulombs constant is 8.99 times 10 to the 9 Newton meters squared per coulomb squared. So when we plug in everything into our formula, we get that our electric field strength is approximately, or actually exactly, 1,726,080 newtons per coulomb. Now, we actually can notice something that will allow us not to do the calculation both times, because we don't have to. We know that both charges, and let me include a direction here, to the right. Both charges are equal distance from point P and have the same magnitude of charge. So, since both electric fields go to the right, we can assume the electric fields are the same for both, but just double this. So, E absolute value of electric field net equals 2 times this value, and this equals now last thing we have to do is round this into scientific notation. So, I'll add 3.0 on both just to make it easier. Since the lowest amount of sig digs is 2 here, we're going to use 2 sig digs in our final answer. So here, the lowest amount of sig digs. So the electric field, final answer, is 3.5 times 10 to the 6 newtons per coulomb. It's a vector, so include direction to the right. So this question you'll probably see somewhere, and you just gotta know when to add the electric fields and when to subtract them. So when they have the same charge, you add them, but when you have opposite charges, you subtract the electric fields using your absolute values also. And usually point P will be in the middle when you have to calculate this. All right, so here we have another example of a non-uniform electric field. And it's asking us a point charge is 0.5 meters from point P and creates a 3.5 times 10 to the 4 newtons per coulomb electric field toward the charge. What does Q include a sign? So the first thing we're going to do is choose the formula we're going to use. And since it's a non-uniform electric field, we know that E equals KQ over R squared. R equals 0.5 meters. K equals, we know, 8.99 times 10 to the 9. And electric field strength, which is given this time, is 3.5 times 10 to the 4 newtons per coulomb. So we want to determine the charge. So we're just going to rearrange the formula by multiplying by R squared on both sides, then dividing by K. So then Q becomes electric field R squared over K. And now we can basically just sub in our values. So then this equals 3.5 times 10 to the 4. Should probably include my units. And when you do this calculation, I've done on my calculator, this is what you get. So that's 9.733. Remember, show your full work on a test and then round it for the final answer. So this would be times 10 to the negative 7 coulombs. So since we have 2 sig digs in the question, we're going to be rounding this final answer to 2 sig digs. So the charge is 9.7 times 10 to the negative 7 coulombs. But we're not done yet, we need a direction. So it creates an electric field toward the charge. So since the electric field is toward the charge, the electric field is the direction a positively charged object will go. So if a positive object goes toward the charge, that means the charge has to be negative, because negative attracts positive. So when we add a negative sign in front of our answer, this becomes the final correct answer to this question. And quick thing, this was times 10 to the negative 7 coulombs, not times 10 to the 7. But yeah, you guys saw that here. Times 10 to the 7 coulombs is something you'll probably never see. That's way too large. Alright, so now we got a different type of question, and it's 3 parts. Just a little bit more. But as long as you follow the steps, it'll be fine. So, A, calculate electric field 4 centimeters from the positive plate. So, first thing you might be thinking to do is, find a certain ratio for the electric field and then see how the electric field changes 4 centimeters from the positive plate. Do some relation. But no, you actually never have to do that in this case. Although you could, no point in doing all that. The electric field strength 4 centimeters from the positive plate is the same anywhere else. So, since we have the distance between the plates, 0.15 meters, and we have the voltage, 1100 volts, we can simply know that we can use that to find the electric field. So that's basically the main thing that mixes students up with this question. The electric field strength is straightforward, the calculation, but just knowing that you can use these two values is what some students are unaware of. So you can just say electric field equals the change in voltage over the change in distance, which is equal to 1100 volts divided by 0.150 meters. And then plugging this in your calculator, we get that it's 7,333.3 repeating volts per meter, and the electric field strength is down. So when we round this using our sig digs, our lowest amount of sig digs is 3. So this would just include down. This would just be equal to 7.33 times 10 to the 3 volts per meter, and then downwards. Okay, that one's straightforward enough. Now we need to find the acceleration of E. So one thing we have to know is that when particles small like electrons travel in electric fields like this, the only force acting on them is the electrical force. And when the only force acts on a body, we know that that's the net force. So we know that F net equals EQ. And yeah, sorry, one thing I should note, FE equals EQ. Sorry. So then we can expand this, and we can say mass times acceleration equals electric field times the charge. Sorry, I should have written FE here from the start, but just know EQ is FE. And now we have the mass of the electron. The mass is equal to 9.11 times 10 to the negative 31 kilograms. We know the electric field from earlier, which is, we're going to use our unrounded values for full accuracy, which is 7,333.3 repeating volts per meter, and our charge is always 1.6 times 10 to the negative 19 coulombs for the electron. So here, what we're going to do is divide by mass on both sides to isolate for acceleration. So acceleration then becomes EQ over M. So the acceleration is equal to this calculation when we plug in the values. Just divide this by the mass. So our acceleration then comes out to be about, haven't done the calculation yet, but we can simply plug in the values. See these projectile motion questions, you just have to take them step by step. So 1.6 times 10 to the negative 19, and divide that all by the mass of the electron, 9.11 times 10 to the negative 31 kilograms. Accelerations in questions like this are usually high, so this makes sense for acceleration. We know that we want to, well, round from here, since we don't have that much space left. We know when we want to round to 3 sig digs, so we're going to round the 8 up in this case. So it's 1.29 times 10 to the 15 meters per second squared. So acceleration will be 1.29 times 10 to the 15 meters per second squared. And we know it's obviously going upwards. the electrical force is up, so the electrical force is causing an upwards acceleration, so we can say upwards. And this would be the answer to part B. Okay. All right, we're doing good so far. So C, what is the horizontal distance of E, or the electron? So this is where we kind of put everything together, start including our kinematics, and think a little deeper. So if we want the horizontal distance of E, here we know we have the horizontal speed, which is constant. So we know that V is equal to d over t, since this is constant speed. So if V is d over t, then Vt is equal to d, but we don't know t, it's missing. So we're gonna have to use some kinematics to find d. Here we're given that the electron has a vertical, it travels into the electric field 7.5 centimeters from the positive plate, and it goes at full 7.5 centimeters. So the displacement is equal to 7.5 centimeters, which is going to be, I think, 0.075 meters. And, sorry. And now that we know that, we also know our acceleration from the previous question is 1.28, 796, 194, 7 times 10 to the 15 meters per second squared. And see, we're finding the time is the same for the vertical and horizontal, so we're going to use the vertical components we have to find the time. So we know that this is our distance, this is our acceleration, and we know that VI y is equal to 0. Now we can set up an equation and solve for time. Whenever you have three variables for kinematics, you can always find the final thing you're looking for, because there's 4 variables in each equation. And any combination of 3 variables you have, there's always an equation to find the missing one for kinematics. So this equation we'll use here is d equals VIT plus 1/2 AT squared. VI is 0, so whatever the time is, when we multiply it by that time, it's going to cancel out, so we'll write 0 here. So that, and we'll also multiply by 2 on both sides. So that means 2d equals AT squared. We'll divide by our acceleration on both sides. So t squared is equal to 2 times our displacement. Divided by our acceleration. And let's square root both sides. So that means time becomes the square root of 2d over a. And essentially now we can plug in our value for time. So t equals 2 times 0.075 meters divided by 1.28. We'll write dot dot dot, but use your, I'm going to write dot 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 to shorten it, but use your full value in the calculation, times 10 to the 15 meters per second squared. And of course, square root of that is our time. Kind of looks like a E. Let's fix that. Okay, that's our time, which is gonna be a small value, of course. Because look, you're dividing this relatively small number by this huge number. And so this is the square of the time, extremely small. It's gonna become a little larger once we actually take the square root of it. And this is the typical range of time you'll get in this. So here's our time, which is 1.079 180,559 times 10 to the negative 8 seconds. In questions like these, it's usually going to be times 10 to the negative 8 seconds or times 10 to the negative 7 seconds. So now we can just say V equals d over t. Recall that. So D equals, well, dx, horizontal distance, equals vt. Now we can sub in our values. Remember, our horizontal velocity, 5 times 10 to the 6 meters per second. And our time is 1.079. (180,559) times 10 to the negative 8 seconds. And so our dx comes out to be, when we put this in our calculator, we have our time here, just times by 5 times 10 to the 6. Horizontal distance is 0.53959028 meters. So our dx rounded to 2 sig digs, or rather 3 sig digs, is 0.540 meters. Sorry, 0.0. Sorry. This is 0.0, guys. It's 0.0. So 0.0540 meters. And just to make it cleaner, we can convert to centimeters. So our dx (5.40 centimeters). And this is the answer to the question. Part A, B, and C are all here. See, these projectile motion questions, you'll usually get it all in one question. It will give you the information, and you'll have to find, for example, horizontal distance, or it'll give you other information and you have to find the electric field strength or something like that. Here I broke it down for you guys to understand it, and now that you understand each step, you can combine all the steps together when you need to.